Hi, welcome to es301 Engineering Analysis. This is chapter 10, LU Decomposition and Matrix Inversion. So here are the three learning goals. At the end of this video, you will understand why LU decomposition can be an efficient solution technique for systems of equations. You'll know how to implement naive LU decomposition, or what I mean is LU decomposition without pivoting. We've already covered how to pivot. And then third, you'll understand how the matrix inverse can be computed using LU decomposition. So first I want to just talk about why LU decomposition is worth it. If you go through this chapter, you realize it's a lot more work than Gauss elimination, and so why would you ever want to do that? And so what I want to do is give you a very common engineering example of why this might be worth it. So over here on the right, what I show is, imagine this is some sort of, for example, a steel plate. And maybe one side of it is hot, and then over here it's cold. And I'd like to know the steady state temperature distribution within this plate. So the equation that I'm solving, if I want to know the steady state, is this equation here, where this is K, the thermal conductivity, del squared T is equal to 0. And if I was to look at this, this was a two-dimensional plate, so imagine it's somewhat thin and two-dimensional, I would write this out as K, and this would be d squared T dx squared plus d squared T dy squared is equal to 0. And if k is constant throughout the plate, it would cancel out. It also could vary in various locations with the plate, in which case we keep it in there. And I'll come back to that in a minute, but let's not worry too much right now. So the equation that I'm solving is a second order derivative here. And I'd like to solve for that numerically. And so what I need to do is I need to determine what is a numeric representation of this second order derivative. And the way I can do it is first is just imagine I have some point, random point in this. I'll call that point there, and I'll give it index mn, so it's some location within the plate. And if I wanted to estimate what the derivative is there, well, if I was to discretize the whole thing, and so this right over here would be mn plus 1, and this would be mn minus 1, for example, just index numbers. What the derivative is there, what I could do is I could take the temperature halfway in front of it and halfway behind it, divide it by this delta y distance, and that would give me a numeric approximation of the first order derivative. All right. Now I want a second order derivative, so what I can do is just do that again. So now what I'm going to do is I'm going to take my first order derivative at this x there, and that one there, and again do this numeric differentiation. So I'm taking this, plugging it into there, and then doing the same expression over here. Clearly I'm using a different pair of indices, and what I end up with is this third term that I have in this equation, where now, in order to know the second order derivative at a location mn, I'm using the temperature there and the temperature in front of it and behind it, right? So now I'm using just what the temperature is in order to determine what the second order derivative of this equation is, right? So that's what we're going to go ahead and do, and that's what we're going to be solving. And you can imagine if I have this fairly large plate that's discretized, I'm going to have a whole bunch of simultaneous equations for the temperature that I want to solve. Okay? Now if I go ahead and finish out the algebra, this is the equation that I have, and what you'll realize is it effectively just says that the temperature at some location mn is the average of it on the left and the right. Because now what I've done is this is d squared t dx or dy squared. I also do the same thing in terms of x squared. Okay, so let's kind of just look at a little more concrete example. So imagine this is my steel plate. I've got some approximate temperatures here. And so what I'm going to do is I'll just do a simple discretization now where I'll have 4 points within the plate that I would like to go ahead and find. And clearly, I also know the temperature at these points because that's specified. Those are what those boundary temperatures are. Okay, so I've got 4 points in the plate I want to find. That's going to give me 4 equations, and these are my 4 simultaneous equations in terms of the temperature and then the index. So this right over here is temperature T11, this would be T12, this is T21, and temperature T22. And if I wanted a more fine grid, I could just end up having more equations. Now if I was to go ahead and put this into a matrix form, this is exactly what it would look like. Where here these functions of 4 are arising from there. And again, you should kind of notice that each time that's effectively saying is a temperature at some location like T11 is just the average of the 4 temperatures surrounding it. Okay? Well, notice these numbers right over here, those are the boundary conditions, and then this over here is just a function of what the geometry is. And I want to come back to that point when we had, remember I had k d squared t dx squared plus d squared t dy squared, and I had this conductivity. If the conductivity varied throughout the plate, and it was made of different materials, I'd actually have various values of K in there at various points within this matrix. But notice the matrix is only representing the discretization or the geometry of the plate and the physical aspects of it, and the boundary conditions are in B. And so if I wanted to maybe solve this equation again and again and again with different sets of boundary conditions, so what would be different temperatures on the outside to find the inside, all I'd be doing is changing this B value. And so you can imagine that if I had a fairly complicated geometry with lots and lots of nodes like I show in this picture down here, I might have hundreds of equations. And if I wanted to look at it, just kind of run a various scenarios where I had different temperatures on one boundary, I wouldn't want to have to do a Gauss elimination on this huge hundreds and hundreds of lines of matrix each time when all I'm doing is changing B. And that's why we're going to see LU decomposition as a way that I only decompose the matrix once, and then I can go ahead and apply all my different sets of boundary conditions by just altering this B vector. All right, so let's kind of look a little more concrete at how you go ahead and implement LU decomposition. So let's first imagine, well, I've got this matrix of equations that I want to solve, and so now using the notation in the book, I've got some values A, and I want to solve for X, and that's all equal to B. Remember, B kind of represents what my boundary conditions are. Now, if I was to do the first step of Gauss elimination, which means that I want to go ahead and get those zeros in the lower left-hand corner, I'd end up with a matrix that looks like this, where I've now altered my values of A on everywhere but the top row, and I've altered my values of B. And this happened because, I remember, I would go and find the factors. For example, to go ahead and set that value there equal to 0, I'd have a factor that would be equal to simply A21 over A11, and I would multiply that equation, the top equation, by this, and then subtract that from the bottom equation, right? So what that would end up doing is changing A22 and A23, and also change B2. Okay. Now, if you look at what would be the effect on B2, well, B2 prime would end up being what B2 was initially minus that factor F21 B1. So I'm going to call this factor F21 because it's the factor that I evaluated when I was doing index B2, or doing index A2. Now, one of the things to notice is that determining the B's, okay, I could go ahead and hold off doing that. I could just go ahead and solve for this value, the A matrix, and then just as long as I remembered all my F values, I could change the B vector later on. And that's what I'm going to go ahead and do. And in fact, what I'm going to do is I'm going to go ahead and do this first part. So I'm going to create a matrix where I've got all of my A values, and they're going to be altered on everything but the first line, so A11, A22, all of those values. And then instead of putting zeros on the lower left-hand side, I'm going to go ahead and store those values of F. So I'll put F21 down here, F22 down here. And I'm going to go ahead and store those in this lower part so that later on, when I want to go ahead and compute my B prime vector, I've got the values stored down here, because normally it's just holding zeros. Well, what this is ends up looking like is two matrices. I've got what's called the upper matrix, okay? And this right over here is the upper matrix. And then I also have a lower matrix, which is the L matrix, which is the one that's got a bunch of 1s down the diagonal, and it's holding all of my F values. So the upper matrix is all those A's and A primes, and then the lower matrix is a bunch of 1s and all of my F values, like that. Now that I've decomposed it into these two vectors, I can then go ahead and be able to solve this several times for different values of B without ever having to change what my U matrix is or my L matrix. Okay, so here's the steps. This is from the book, and I want to kind of explain these steps because this is where I said LU decomposition on the face of it looks more complicated than Gauss elimination. And actually, it's just implementing Gauss elimination in a couple different steps. Okay, so here, this first one right up at the top, this is what I'm trying to solve. I have my matrix A, my vector X, and that's equal to a vector B. And so the way the book uses in terms of notation, the curly brackets means that these are vectors or column matrices, and then A's would, for example, be a square matrix. Right. So the first thing I do is I decompose it into this upper and lower, and that's the steps that I just talked about, where the upper has all my A values and the lower stores all of those F values in it. And then remember, I held on to B. I didn't evaluate or didn't go ahead and alter my B value. And then what I'm going to do is I'm going to solve this equation. I'm going to take my lower matrices. I'm going to find out what D is. So some vector I could multiply that would give me D. This turns out this is the B prime vector. The book uses notation D. It turns out this is just what the values of B would have been if I'd done Gauss elimination at the original step. And so at that point, once I have D, which again, you can think of it as just B prime, once I have that, I can now go ahead and solve for X, this original X I had at the very top using my upper thing and back substitution, the second step of Gauss elimination. And I know what D is, which again, I said it's just effectively B prime to find the value. So you look at what I've got is two steps of Gauss. I do my first step of Gauss up at the top, then I have this intermediate step, and then this is the second step of Gauss. So it's just a little intermediate step in terms of finding B prime. And it's actually not much more work. I'm just breaking it into parts, whereas before we kind of did this all at once. Okay, I want to talk a little bit about what would be called forward substitution. So this is the step where I'm trying to find the D vector, which is effectively B prime, trying to find that vector using this. And so this is my L matrix, the lower matrix. I have ones down the diagonal and then those factors that I have in there. And what I'm going to do is just go ahead and compute it. I'm doing forward substitution. I'm going to start at the top and go down, but otherwise it's just like we did with Gauss elimination. I take this first one, and this first equation is pretty simple. It just says D1 is equal to B1, right? And that's where we never altered that top row of B because we didn't do any substitution on it. And then if I look down at the second one, what I have is I have this factor F21, which I went ahead and stored, times D1, which I just computed, and I know that, plus F2, or 1 times D2, and that right there is going to be equal to B2. And now I can go ahead and solve for D2, and then keep going down, and D3, etc. Now I have my vector D, and this is what I'm going to multiply by my big U matrix in my forward substitution, right? So this D matrix that I just found goes into here. Now I'm finding what my value of X is from my modified A. This is the upper matrix that I held on before. And so now I'm going to go ahead and compute this D. These two steps here are what change every time I have different boundary conditions. The first step I only do once, and then every time I have a new set of boundary conditions, a new set of B's, I find a new set of D's, and then do this step. So this one, again and again and again. But I don't have to do that first part of Gauss elimination of forming the upper matrix other than just once. Now, I want to talk about one more use of LU decomposition, and that's in terms of finding the matrix inverse. So first let me remind you what the matrix inverse is if you're not familiar. So imagine I had this system of equations. This is kind of what we've been trying to solve the whole time. We have this system of equations that represent as a matrix times a vector equal to a vector. And I could write this in kind of vector or matrix notation as this way. AX is equal to B. And what, in terms of my notation, I'm using a capital letter, meaning that this is a matrix, and then lowercase letters in terms of vectors. Okay? And now we're only going to be talking about square matrices at this point. And it turns out that most problems are square. Any of these engineering equations, like that temperature one I showed you, will always end up with a square matrix. All right. So I'm trying to solve this. Now this is looks like an algebraic equation, but it's written in terms of vector notation. And what it can do in terms of the algebra on here, I can pre-multiply both of these by some, for example, some vector, some matrix. I'm going to multiply it by a matrix, and I'm denoting A minus 1. That's called the inverse matrix. I can multiply this by any square matrix that I want. This would be a fine thing. I'm just multiplying both sides of the equation by the same thing. Now, if it turned out, if I had found a vector that I'm going to call A1, such that when I multiplied it by A, because the rules of algebra in here with matrices is you go from left to right, A prime, A to the minus 1 times A. If I did that such that that would equal a matrix that just had a bunch of zeros in the upper and left and ones down the diagonal, that's called the identity matrix. And note, if I was to multiply the identity matrix by x, x1, x2, x3, etc., since all I have are ones there and zeros, this is effectively just the x vector that I want. So what this says is that A to the minus 1 times B is x, which is what we're trying to solve for. And now I don't have to do Gauss elimination. This is just a forward multiplication, because I know what A to the minus 1 is, and I know what B is. So this is the matrix inverse, and it sure would be nice to find that, because then I could go ahead and for whatever values of B, those could keep changing. I could go ahead and find my value of x just by forward multiplying that. All right. Okay. So let's talk about how you find that inverse matrix using LU decomposition. This is the way you do it. So this is my A matrix that I want to find the inverse of. Okay, and what I do is I set this equal to a vector that's 1, 0, 0. Put 1s at the top and 0s everywhere else in the bottom. All right. Now go ahead and solve this for x. And then what I'm going to do is I'm going to take that vector and put it right here. So this is the value of x. I'm going to put it in there. This is I'm going to build my inverse matrix, a to the minus 1. So the first column is when I went ahead and put a 1 on the top. Then I'm going to set it equal to 0, 1, 0. And you can probably guess that's going to be the second column. And then I'm going to set it equal to 0, 0, 1. And that right over there would be the third column. And no matter how large my matrix is, here I'm looking at 3 by 3, but I give you 100 by 100. I would just do that 100 times. And notice this is really easy to do by LU decomposition, because what I'm doing is I'm just changing the right-hand side. I'm effectively just changing my B vector. I'm changing it to these very simple vectors where I just have a 1 value surrounded by a bunch of zeros. All right, so let's review what we talked about in this video. We looked at LU decomposition, and we saw it can be efficient when we're solving similar problems that have differing boundary conditions. We saw that LU decomposition results in taking that vector, or sorry, the matrix A, and then generating two different matrices, which we call U and L for upper and lower. And we have the lower one has these factors F5J that we go ahead and store in that lower matrix for later, and that way we can go ahead and preserve B and then generate our new B primes, which the book calls D later on. If we know the matrix inverse, that permits direct solution of a set of simultaneous equations. We don't have to do Gauss elimination again and again and again, and we'll do it once. And then what we saw is that LU decomposition would be an efficient scheme for finding that matrix inverse, because in order to find the matrix inverse, all we're doing is changing the B vector on the right-hand side.